Okay, good morning. Just wanted to give you a little bit of explanation about some of the apps that you have to possibly choose to parallelize this semester, starting with the digital music analysis app. This is an app that was created by a student working with me a couple of years ago, or a few years ago. It's designed to help beginner violin players. If you don't have a teacher present when you're trying to practice, it's very hard to tell whether you're actually playing a piece correctly or not. So you've got some sheet music, as we see here, with the various notes that we're meant to be playing. Now, the difficult thing about trying to play these different notes on an instrument like a violin, which doesn't have keys or frets marked on it, you have to know precisely where to place each finger on each string in order to play these different notes. Now, it's possible to have your finger in approximately the correct position, so you'll still play a C or a D, for example, which is what you're meant to play, but perhaps if you've got your finger a millimeter higher or a millimeter lower, it'll be a little bit sharp or a little bit flat. Now, a trained teacher is going to be able to hear that and be able to give you feedback that it's a little bit sharp or a little bit flat, but it's hard for a beginner who's just learning music to be able to hear the difference. So this app is designed to give feedback to the beginner player when they don't have their teacher present. So the aim is to be able to play a piece like this, record it digitally on the computer, and to have the computer analyze what's been played and give you feedback in terms of what was right and what was wrong. So a little bit about a bit of theory in terms of music and sound. Sound is, of course, a sound wave. It has a sine or cos type shape to it, and it has some sort of frequency. So this is the time going here from left to right, and different notes are made by having different frequencies or different length of the wave. So this particular wave here has got a certain length, and if we play it, this is the middle A, which has a frequency of 440 hertz. So it's 440 cycles per second. This wave repeats 440 times every second. Now, on the staff, that would be marked as this A here, which is the A above the middle C here. So on a piano, it would be this key here, just a little bit to the right of the middle C in the middle of the keyboard. Now that's as you heard, that pure A tone is very synthetic. It doesn't sound very pleasing to the ear. It sounds like it's computer generated. Doesn't sound like the sort of note you'd get from a musical instrument like a piano or violin. And in order to generate real music on an actual instrument, you don't get single frequencies. You have a combination of frequencies that come from the natural harmonics which the instrument produces. So we always have a combination of different frequencies being played which combine together to give this richer sound. Okay, so that all of the music is defined, or these different notes, these different pitches are defined based on this middle A of 440 hertz. Now, if we go one octave up to this higher A, it's going to have twice the frequency, so it's going to repeat 880 times per second. And if we go down the scale to the next lowest octave, this A here, it's going to repeat 220 times per second. So you can have this blue wave here, a very long wave, which will have a low sound, and the higher one, which is repeating twice as often as the 440 hertz, which will be a much higher pitch. So they're all A's. This is a middle A, a low A, and a high A, but they're all referred to as A. So once we've got those A's, they enable us to then define all the other notes on the keyboard or on the keys. So if we have between the low A and A3 and the middle A, A4, which range from 220 hertz to 440 hertz, we divide that interval into 12 equally spaced notes. Now, when we say equally, we don't mean in a linear way. We mean if we take the log of this number, the log base 2 of this number, and the log base 2 of this number, they'll differ by precisely 1. So if we take that log space of 1.0 and divide it by 12, we'll get these equally spaced intervals here. So it gives us the notes from A sharp, B, C, C sharp, D, all the way up to the A in the next octave. And we can repeat that process for all the octaves. If we go from the middle A to the higher A, from 440 to 880, again we divide that octave into 12 equal notes, and that gives us each of the notes, each of the 12 different notes in that octave. Now, we can in theory go up an infinite number of octaves and down an infinite number of octaves, but the human ear can only perceive a limited range of octaves. We can't hear really low, or we can't hear really high octaves. So when it comes to digitally recording audio, what we have is the red wave. That's the actual wave that's coming into the computer. And if we're recording this on an old vinyl analog recording, we would have the groove in the record capturing the shape of this analog wave here. But if we're going to do digital recording, this gets sampled. We sample what the value of this wave is a number of times per second. Typically it's 48 kilohertz or 44.1 kilohertz, which means every second we create 48,000 samples. And each sample is then digitized, turned into a positive or negative number, either an integer or floating point value, depending on the digital format. It's going to be then rounded depending on the number of bits we use per sample. This is an extreme value here where we only use 4 bits per sample. So this wave here would be turned into this sequence of positive and negative numbers here, which are the values of this wave, say -4 here, then 0, then 4, then 7. So you see this 7 here, it's not quite 7. That 7's a bit higher than what the wave is, but it's closer to 7 than it is to 6. So there's this rounding process when we turn an analog signal into a digital signal. Now, the trick then, once we've got this digital audio recorded and read into the computer, is to work out what note is being played, or what frequency. But as we said before, there's typically more than one frequency that's being played at any one time. So if we take a frequency of, say, 50 hertz, represented by this wave here, what tends to occur, based on the way that the sound bounces off the various surfaces within the instrument, you'll get other frequencies being produced as well. The most common one would be the first harmonic, which would be twice this frequency. So 100 hertz, which would be repeating twice as often as this one here, and to a slightly lesser extent you might have a second harmonic, which is 3 times the original frequency. Now, you're not just going to get these pure first and second harmonics, which, if say this is a C note, you might also get some a G as well being played based on just the natural harmonics of the instrument. So even though you as a musician you play a C, you might get a tiny little bit of G being naturally produced by the instrument. So it becomes quite complex to reverse engineer from the wave back into what the actual frequencies are, because all of these individual frequencies that are being produced, they all get summed together. So if we take at any particular point in time going from left to right, if we sum this wave plus this wave plus this wave, each of these are nice sine curves. They're very mathematically symmetric, but when we add them all together, we get something quite irregular like this. And this is much more typical of the sort of recording that you'll get when you record actual music notes. Even if you are playing just a single C note on a violin or a piano, forget about chords, just a single note is going to produce sound waves like this here. And our challenging job then is to turn that wave back into its the frequencies that make up that signal. Now, to do so, we're going to draw into mathematics, developed centuries ago by a guy called Fourier. He developed this way of transforming from the so-called time domain. So this data here is what we call in the time domain. So we have time going from left to right. We sample the sound at various points here, and at each point we measure the amplitude of the wave. Now the amplitude, of course, is the volume. The higher these waves are, the louder it will be, and the frequency of the wave represents the pitch, whether it's a high note or a low note. So we take this time domain data where we've got a amplitude value at each point in time, and we apply what's called a Fourier transform, and it's going to turn that into the so-called frequency domain. It's going to say at some particular interval of time, say from this point in time to this point in time, on average during that period, the actual frequencies that were being played were 50 hertz. So if we took a Fourier transform of just this wave by itself, we might get this data here. We'd have a peak at 50 hertz and the equivalent of minus 50 hertz based on the way the complex numbers work here. And similarly, if we did a Fourier transform of this first harmonic, we'd get peaks at 100 hertz and slightly smaller waves. These first and second harmonics tend to be smaller than the fundamental frequency, and we got peaks at those points as well. So if we did that's what would be expected, but the magic of this Fourier transform is we can do it not just for these pure single frequencies, but we can apply this Fourier transform to a sound wave that's actually made up of a combination of frequencies, and it'll work out what each of those individual frequencies are. It'll say, well, it was mostly mostly 50 hertz. So there's a big peak here at 50 hertz. There's a slightly smaller peak at 100 hertz, and there's an even smaller peak at 150 hertz. So we can get this frequency spectrum where for each different frequency we can get what is the amplitude measured in decibels for that particular frequency. So here's an output from the app. We jump back to the app. So this is showing at some particular point in time over each of the different octaves, it's showing which frequencies are most frequent. So we have a peak here around about a B. So it's a little bit higher than a B, but it's certainly not a C. So this is an example of where a note was probably meant to be a B. Down here it's actually perfectly on B, but in this next octave up, it was tending to be a little bit higher. Now, part of this depends on how we do the rounding as well. This is of course a discrete digital analysis, so if we did it a bit more fine-grained, we might get more detailed results as well. So ultimately, the goal is to show the sheet music. This is what the black notes are, what we were trying to play, and perhaps the red notes is the ones we got wrong. So we put our mouse over here, we see, well, that was good, we were meant to play a D, and the actual frequency, which we can see down here, is 585 hertz, which is exactly what it was meant to be, which is a pitch error of 0.002. So we got this one quite right, but this next one here, we can see it was 16% too low compared to what it was meant to be. We can also get some feedback via these boxes here in terms of whether or not we played the correct duration. So this note was meant to be twice as long as this note, which it was. So the red and the black line up, but in other cases that may not be the case. Okay, so how do we do that? We make use of this Fourier transform. Now, the Fourier transform is just going to give us a breakdown of the frequencies for some period of time. Now, this is a indication of the Jupiter song that we've read into the app, and we can see over time the frequencies that are being detected are going to change. So we can see from this point in time to this point in time, pretty much that's all very uniform. So it's all from here to here, it looks all very the same. Whereas you can see here there's a slight gap here, and then we seem to have played the same note again. So we seem to have played a long note, a slight pause, and then another long note, and then the same one again, and then it's gone up to a slightly higher note for a shorter period of time. So we can see the length of the notes here. Some are short and some are longer here. This y-axis here is your different frequencies. So we can see repeating here, 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 here. Each of these are probably different harmonics. So this might be the fundamental harmonic, and we get twice that, and twice that again, and twice that again, as well as some other ones being mixed in. So how do we get this data in the first place? So what we're going to do is take this period of time. So the song plays for maybe a minute, and we're going to break that minute up into tiny little intervals, and we're going to do a so-called short-term Fourier transform. So we might take, say, from this period of time here to this period of time here, just a fraction of a second, and we're going to apply a Fourier transform to work out during this tiny little interval here what frequencies were being played. And we're going to do that for all of the entire song, breaking it up into tiny little intervals. And that will tell us for those tiny little intervals what combination of notes were being played. Now the trick then is to work out, well, when do we actually transition from one note to another? We can see going from this point here to this point here, we've had a change in note. You can see that the frequencies have changed quite a bit here. So mathematically, it's actually quite challenging to do this. So that's referred to as onset detection. We want to tell when one note is finished and the next note has begun. So if we were clever, the algorithm would say, okay, there's one note finishes here, another one starts, and there's a change here, and here, and here, and here, and here, and here, and so on. Once we've worked out when each note starts and finishes, we're then going to do a more precise Fourier transform to work out, not just for one tiny little interval, but for the entire note, what frequencies were being played. So if we go from this point here to this point here, and we average over that entire period, we'll get a much more precise indication of what note was being played compared to if we just analyzed one tiny little fraction of a second. So we'll then get an indication for each note what combination of frequencies made that up. So let's have a look at the code that does all of this. So we jump to the main function. We've got a constructor down here which does most of the work. We first read in the files. So we read in the wave file, which is our digital audio file. That just gives us the name there. We're also going to read in the name of the file. We're also going to read in the XML file, which contains the sheet music. Okay, so we're going to create a thread here, just so that as the song is playing, we can keep the little slider up to date with where the music is currently playing. It's not a particularly crucial part of the app, it's more for diagnostics, for trying to improve the algorithm. We're then going to take this audio file that we've got the name of here, and we're going to load it in. So we're going to parse the digital audio file and read it into a big array, basically. And here we're going to do most of the heavy lifting. So this is frequency domain, is where we did all of that stuff that I talked about. So it does both the short-term Fourier transform. So we can see down here, we're going to do the onset detection. So this is going to determine when one note starts and the next note begins. But it's going to be based on the short-term Fourier transform, or short-term Fourier analysis that we do in here. So this is going to be analyzing the data that we just read in here. So let's have a look inside of this frequency domain, and all of the work here is really done by this this other class. So there's another class called the time frequency class. It takes as input this wave file, which is, as we can see here, just an array of floats. It's a big array containing the whole song, and this here says we want to actually break that song up into tiny little intervals of 248 samples. So remember, there's 48,000 samples per second, so a period of time of 2,048 samples is only about 1/24th of a second. So it's a really tiny fraction of a second that we're going to repeat this analysis. So all of that work is done inside of this class here. We'll have a look at that in a moment, and it returns the result into this, which is a short ST is for short-term Fourier transform. This gives us back a field, a class that we can use, and all this code here is really doing is turning it into a visualization. So it's taking the time frequency data that we have here, which is a two-dimensional array, and basically displaying it, basically designed to create this. So this here is just a big pixel array. The white color is a high intensity, the black is a low intensity. So the white would be a high decibel, the black would be 0 decibels, meaning no components. This is the frequency axis, and this is the time axis. So we just create a big bitmap basically, and display it here. We can scroll in if we want to see it in more, zoom in if we want to see what's happening in more detail. And again, this is largely for diagnostic purposes. It's not really the end result. What the beginner player is going to care about is not what it's going to look like in this space, but what this is going to look like here. So the actual musician cares about the staff, the notes displayed here, and an indication of what they've got right or wrong. This tab here of showing what the different breakdown is, and this one here, this is just the raw data. These tabs are just designed to be diagnostics to help us develop the app further. Oops. Okay, so we've done with frequency domain. As I said, this is just working out the pixel array. If we go back to our main function, after we've done the frequency domain, we then read in the sheet music, which is XML in its format, which is here's the actual Jupyter piece. So it's just an XML way of capturing that sheet music. So we had back so we started with something like this, and if you're going to store this here in a digital format, there's apps such as MuseStore, which will turn that sort of input into a digital form. And if we scroll down here, we see that so we can see the very first note. There's a note here, and the pitch of that note is a B in the third octave, and the duration of that note is going to be length 2, which is an 8th duration. The next note is a D in the next octave up, in octave 4, and it's going to also be of duration 2. Then you've got an E4, which is twice the duration. It's going to be a quarter note, which is of duration 4, twice the length of the previous note. So this can be parsed and read into the program. Okay, so we read that XML file using this XML parser, and the next step is then to do this onset detection, determine when does one note start and when does the next note finish. And pretty much the rest of this is just visualization. To actually play back the song and display the graphics is just diagnostics. So the main work of the system is completed in this onset detection. So if we look at the onset detection, we forgot to have a look in the frequency domain. So let's finish up in here first. So the frequency domain. So as I said, most of the work's done here, which we forgot to have a look at. So let's have a look at this time frequency class and see how it works. So it takes in a big array. It's got a sample for every 48,000 samples per second for the entire song. And this here says we're going to sample or break that time interval up into 2,048 samples per second. Now, the Fourier transform works with complex numbers. So you can see here we're creating an array of complex numbers, and we're pretty much copying this x, which is the array of floating point numbers we passed in. we're going to copy that into our complex array. So we're just converting from this, so complex x is of type complex, x is of type float. So we just assign a float to a complex, which just means the imaginary part of that complex number will be 0. And we need to just pad the remaining with 0. We need to make sure that the length here that we're dealing with, the period, if it doesn't divide evenly into 2048 samples, we just need to pad the rest with zeros, because we always need a power of 2 in the length of the array when we're doing these Fourier transforms. So this is our data, which is just the complex version of our real data, and that's going to be passed to this function here, which does the short-term Fourier transform on this complex number based on a certain sample rate. So you can see the implementation of this short-term Fourier transform is down here. It takes an array of complex numbers and a sample, and it's going to return a two-dimensional array. So that really corresponds to that bitmap, really. In one dimension you have the time axis, and in the other dimension you have the frequencies. So at each sample we want to know what the intensity of each frequency is. So it'll be represented in this return value here. Now the way this Fourier transform works is to, again, most of the work's going to be done by this Fourier transform function here. So before we call the Fourier transform, we just need to do some setting up. So this here is going to loop over. We're not going to do this Fourier transform for the entire song. We're going to break it up into little parts. So this I loop here is doing each of those intervals. So when II is 0, we're going to do the first 2048 samples. When II is incremented to 1, we'll do the next 2048 samples. In fact, if I remember rightly, there's some overlap. So there's some overlap in those windows of 2048. So we actually overlap slightly by a half. So we copy then from x, which is our input array of complex numbers. We're copying just the part we're going to sample, so just precisely 2048 copies. So we're taking a slice of this input array and copying it into our temp and doing a short-term Fourier transform just for that one part of the array and storing the result back here. Once we've finished, there's going to be just a normalization step. So we just loop through the output here, and we take the absolute value of each value in the result here. So this is a complex number, so we combine the real and complex parts of this number to create the magnitude of the result, and we find the one that has the highest value. And we're just going to use this max here just to normalize. So all of the results in this final result here are going to be obtained by just dividing by the max. So this final result here will give us a value between 0 and 1, so that we don't have an arbitrary scale for the outputs in terms of the intensity of each frequency. But again, most of the work, the actual short-term Fourier transform, is done by this FFT function here, which is implemented down here. So it takes an array of complex as inputs and returns an array of complexes. So this array here is in the time domain, and this result here is in the frequency domain. So each element of this array corresponds to a point in time, whereas each element of this array corresponds to a different frequency. So the magic is quite short. It's quite easy to implement. It's only a few lines of code, and basically it's a divide and conquer algorithm. So we're going to take this input array x, and we're going to divide it into the even elements of that array and the odd elements of the array. So we're going to create two subarrays, even and odd, which are both half the length of the original, and we're going to copy all of the even elements of x into the even array and all of the odd elements of x into the odd array. And then we recursively call FFT, which is the function we're currently in. So make recursive calls on the even elements and the odd elements, producing E, which is the result of the Fourier transform on even, and O, which is a result of the Fourier transform on odd. So again, even and odd are still in the time domain, but the E and the O now are in the frequency domain. So we then just need to, having divided the work into the even and odd parts, we need to then combine those two sub-results back to produce the frequencies for the entire period of time. So the result Y is computed here, which is done by combining the even elements and the odd elements, and there's a little bit of mod calculation here, and multiplied by a twiddle. So this is a little bit of the magic of Fourier transforms. This is some constants that are set up at the beginning inside of this time frequency function. So this is where a lot of the work happens. If you profile this, you'll see a lot of the work is being done in here. Now, divide and conquer, of course, has to stop at some point. So we check to see n here is the length of the input array. If the length of the input array is only 1, obviously we can't divide it into the odd parts and the even parts because there won't be any odd parts. So at some point we've got to stop, and in that case the answer, y, the single frequency of x here, is simply taking the value of x at that input. So there's no work to be done in the trivial base case. We just need to make sure that the recursion stops at some point. We don't keep on calling Fourier transform time and time again. So that's how our short-term Fourier transform works. If we go back up to our main function now, we've done our short-term Fourier transform. We've now read in the sheet music, and we're going to do this onset detection. So we've got a two-dimensional array that tells us for each time sample what the different frequencies are, or the intensities of every frequency, and we're going to go through and basically find the peaks. So just trying to remember how this works. Yeah, so this here is determining when each node is starting and when each node is finishing. So here we've found the end of a note, and here we've found the start of a note. So we're going to add each of those periods of time so that we now know when each note starts and finishes. Now, once we know where each note starts and finishes, we're going to again do a Fourier transform based on the entire note. Now we know precisely when the note starts and when the note finishes. We're going to do a longer term Fourier transform. Rather than just 2048 samples, we're going to do the same Fourier transform type process, but on a typically much longer period. The code is actually separate. It's performing logically the same step, but for whatever reason the student decided to implement it separately. So again, we have a call to the FFT, not the same FFT, a different function in a different class. The other one was in the time frequency class. This Fourier transform is not a short-term Fourier transform, but it's still applying the same process. So it's based on the complex numbers we get from here. And yeah, so once we've done this Fourier transform, that's going to tell us for that particular note all the different frequencies, and we then go through all of the different octaves. So for each octave, from octave 6 to octave 1, we do a check to see what the highest intensity is. So we find out the frequency, which is the highest intensity, and we use that to determine the note. So this pitch here is an array or a list of pitches, and we're going to add what we've determined to be the frequency of that note to this array of pitches. And then of course we need to visualize it later on. So again, the Fourier transform happens here. Same basic process as before. We divide and conquer the base case, the even and odd, recursive calls to the two parts, same exact algorithm as before. So those two pieces of code could probably be combined if we wanted to. So that's pretty much the end of the story. So if you have any questions about that, please post your comments and questions on Facebook. Thanks.